This is a neural network and it is currently learning. Theoretically, if big enough, it could map any function. It could be linear, or the squared, or some really complicated function that I've never seen before. So, how do you build one of those? The answer is linear combinations. Take your data and multiply by some weights, add a bias, and you have reached the hidden layer. Change the weights, change the bias, and you've got yourself another node in the hidden layer. So now that you are familiar with the idea of running linear combinations, let's take a step back and see an even smaller network. Here we have only one node in the hidden layer. This linear combination of our data can be written as a matrix multiplication. We need a vector for our data and a vector for the weights. The bias can also become a vector, and a similar process will happen for each star. If the network expands, we have already seen that we need some other linear combination. It also depends on x1, x2, but some different weights and some different bias, and we will get to h2 star. To express it as a matrix multiplication, we keep the x vector, but the w vector must expand in another row. The bias vector expands in another column, and the same goes to the hidden layer vector. We have been treating things as if x1 and x2 only had one observation of data, but mostly this is not true. What typically happens is that it has more observations. But if you consider that a row vector is one observation of your data, you only need to expand it in rows to see more observations of your data. The same goes to the bias, and the weights is already in good shape. What I've been hiding from you is that the true hidden layer is actually the H star vector with some function applied to it. It is called the activation function. Let's get rid of the full expressions of the matrices and show it in a much more compact way. We take some vector x multiplied by some vector of weights transposed, add it with some bias vector, apply the activation function phi, and we get to the hidden layer. So what do we do from here? If we are at the hidden layer, you basically run the same linear combinations, but with different weights and biases, and you apply maybe some different activation function to get to your prediction y hat. So now I invite you to consider what happens to the network from the hidden layer to y. Notice how we are performing regression, but our features seem to be the values extracted from the hidden layer. So essentially, what the hidden layer is some new mapping of the original features that, as we will see, they are better at explaining why when compared to the original variables. So apparently, we only have to pick the activation functions. There are many options for this. It could be the linear activation function, which implies doing nothing. There is the famous rectified linear, for which you transform every value below 0 just 0 and keep it the same otherwise. But in my opinion, the most interesting activation functions are nonlinear functions. The sigmoid and the hyperbolic tangent may seem very similar, but notice how the sigmoid goes from 0 to 1 and the hyperbolic tangent from -1 to 1. Apparently, we know everything we need to jump into the code. First, we define a sample size and a seed, so every experiment runs the same. Then we generate some random data points, x1 and x2. We combine those as a matrix. We define y as the complicated function we have seen before. The trick here is to add some noise to y, as in real-life scenarios, you typically won't be able to model a perfect function. You will always have some random noise that you cannot explain. So now, y is actually a random variable, and it has the mean as the function we defined. A detail worth noting is that the variance of a sample extracted from y should be approximately 1 by the definition of the random variable. We will come back at this later on. Now we define the activation function. Let's pick sigmoid. The linear combinations thing I just showed you before is called feed forward or inference. To implement it, we need the data points, we need the weights and biases that gets us to the hidden layer, and we also need the weights and biases that takes us from the hidden layer and gets us to our prediction. Let's assume the weights are already transposed. Basically, we run some matrix multiplication and apply the activation function, so we get to the hidden layer. Then we do the same process once again and we get to our prediction. And that's it. We run feed forward. What we are missing is the weights and the biases. Consider our initial guess where the weights are all ones and the biases are all zeros. We now run feed forward, we get our predictions, and we must evaluate if those are good or bad predictions. So we are also defining a loss function, which is the MSE that stands for mean squared error. And what we have got is a value of 203. Is it good? Is it bad? We need some other value to compare. So before that, why even to pick the MSC and not some other loss function? Looking at the MSC expression, we can see that this looks like the sample variance formula. If n is big, n minus 1 must be really close to n. So the main difference is the term that took place of y hat, which is the expectation of y given the data that we have for this given point. However, we already know that y follows a normal distribution where the mean is actually the complicated function we are trying to estimate and has variance 1. So the expectation of y given the data points is actually the complicated function we are trying to estimate. And the coolest thing about this is that the variance is minimized when yi gets subtracted by the mean of yi given the xi values. This is why it is defined like this. So what this shows us is that if we are trying to minimize the MSC, the best prediction we can make is to actually predict the complicated function we are trying to estimate. It implies that if we find a function that has a lower MSC, our predictions must be closer to the function we are trying to estimate. And now, by knowing all of that, remember that the sample variance must approximate 1. So the minimal MSC also approximates 1. A 203 MSC now seems quite bad. Can we make it better? Yes, we can. Our prediction has been defined as the sigmoid function applied to y star, but this must be in the interval 0, 1. My question is, does y lies in the interval 0, 1? Since we have the actual function that generates y, you can show that no, it doesn't happen. But in real-life scenarios, you typically don't know the function that takes you from the data to the actual outcome value. An easier way to approach this is by using some statistics. You could calculate the minimum, the maximum, and the mean of your data. So now, empirically, we know that y doesn't fall in the interval 0, 1. So picking sigmoid was a clear mistake, since it cannot represent the scale of our data. So let's remove it, and now our MSC has gone slightly lower. But we can do even better by using derivatives. Derivatives can directly help us on minimizing tasks. If a derivative is positive, such as that from f of x equals x, then as x grows, f of x must also grow. This also means that if x decreases, then f of x must decrease too. F of x equals x squared not always have a positive derivative. If x is negative, then the derivative is negative. If x is positive, the derivative is positive. If the derivative is negative, it means that as x grows, f of x must decrease. If we are looking for lower values of f of x, the derivative gives us the direction we must go. By definition, the derivatives of a function shows us how fast the function changes. It shows us not only where to go, but how far should we go. To use this idea to optimize a loss function, we need to note that it is a function of theta. Theta is the set of parameters we are using to do inference, to do the feed-forward step. Since we cannot change the data, all we can change is theta, so it makes sense to differentiate the loss function with respect to theta. Since this is a multidimensional vector containing all the derivatives with respect to theta, we call it a gradient. And because we are trying to minimize the MSE, we call it gradient descent. To make clear what theta really is, let's analyze our feed-forward step by step. To reach the hidden layer, we need some weights and biases, and then to reach our prediction, we need some more weights and biases. And that set of weights and biases is theta. Consider any loss function L. If we want to differentiate L with respect to the first weight, how should we do this? Because L is a complicated expression that depends on W1, the best thing to do is to use the chain rule. Our loss function is a function of y hat, and y hat is a simpler function of W1. But then y hat is also a complicated expression that depends on W1. But y hat depends on y star, and y star depends on W1. If we keep going with this process, we will eventually reach a point where we are differentiating H1 star with respect to W1, and this is really easy to calculate. Specifically for the MSE, differentiating the loss function with respect to y hat is pretty simple. Y hat with respect to y star is the simplest one. We chose the identity function, so this must be 1. I'm not gonna walk through every derivative, but there is one that's really interesting. And this is h1 with respect to h1 star. By using the definition of the sigmoid function, we will reach some complicated expression. Let's simplify as most as we can, and then there is a trick. You may note that 1 plus e to the minus h1 star to the minus 1 is actually the definition we have for the sigmoid function. But hey, since this is to the minus 2, we can see that this is just h1 squared. And now that we know that the other term, e to the minus h1 star, we can add 1 and subtract 1 to make it similar to the sigmoid expression we had before. And then we can see h1 to the minus 1. So now you distribute h1 squared and you end up with h1 times 1 minus h1. Why is this interesting? Well, because we need to run feed forward to reach y hat in order to get the loss function and its derivatives. So this means that we already run inference and we already calculated h1. So we can use that result to run a simple multiplication instead of the complicated exponentials we had before. To optimize the gradient calculation, what we need to note is that some derivatives may repeat themselves because of the chain rule. What this means is that we can prune some calculations by actually calculating it only once, and that optimization is what we call backpropagation. The code for backpropagation starts from inference. Then we calculate the derivatives we need, obtain the gradients, and update weights and biases. Note that there is an argument, LR, that stands for learning rate. It is used to carefully update the weights and biases so model predictions doesn't diverge from what we expect. Now it is just a matter of running the algorithm multiple times. The results show that the MSE is in fact decreasing over time. However, at some point, it stopped decreasing significantly. Maybe our network is too small, so let's try a bigger network. Simply using a bigger network doesn't seem to be the way. The solution for this problem actually lies in some other aspects of machine learning. But this video already took too much effort, so we are going to wrap it here. If you enjoyed the journey so far, please leave a like and comment if you would like to see a part 2 for this series.